Okay, fellas, today we are doing advanced networking for hackers. We're talking TCP/IP, DNS, and the OSI model. I'm going to try my best to give you the full guide. Everything you actually need to know, including the advanced stuff. Now please, pros, don't get bored. I know I have to start with the basics, but we will get to the deep dive, so just fucking wait. Trust me, the wait will be worth it. And one thing to remember, I'm going to focus a lot on the OSI model because that is where the real hacking concepts live. Let's get started. All right, let's start with the grandfather of everything, TCP/IP. Now, you can read 1,000 pages about this in a boring textbook, but here is the only thing that actually matters. TCP/IP is the language of the internet. If two computers want to talk, whether it's you watching this video right now or a hacker breaking into a bank server in Switzerland, they have to speak TCP/IP. It stands for Transmission Control Protocol and Internet Protocol. But honestly, don't worry about the name. Worry about what it does. The part we care about most right now is the transport layer, specifically TCP. Why? Because TCP is reliable. It's polite. When your computer sends data using TCP, it wants to guarantee that the other side actually got it. It does this using something called the three-way handshake. Imagine you walk up to a stranger on the street. You don't just start shouting your life story at them. That would be weird. Instead, you do a handshake. First, you say hello. That is the SYM packet, or synchronize. Second, they say, hi, I hear you. That is the SYM ACK packet. And finally, you say, great, let's talk. That is the ACK packet. Once that happens, a connection is established, data flows, and everyone is happy. Now, here's where it gets fun. We hackers look at that polite, reliable handshake and we see a weapon. We can abuse every single step of that process. Think about port scanning. This is exactly what tools like Nmap do when you run a stealth scan. I send the server the first hello, the SYN packet. The server replies with hi, I hear you, the SYN ACK. At that exact moment, I know the port is open. I have the intel I need. But instead of being polite and finishing the handshake, I send a RST packet, which stands for reset. Basically, I hang up the phone immediately. Because I never finished the conversation, the server usually doesn't log the connection. I get my information, and I stay invisible. Then you have the denial of service attacks, like the SYM flood. Go back to that handshake. Imagine if I send 1 million hello packets per second to a server. The server hears all of them, and it replies, hi, I hear you to every single one, but then I just ghost it. I never reply back. The server is left hanging, waiting for a response that is never coming. It's like ordering 1,000 pizzas to a random house and never paying for them. The shop makes the pizzas, sends the drivers, and wastes all their money waiting for a customer who isn't there. Eventually, the server runs out of memory holding these fake connections open, and it crashes. And finally, we have IP spoofing. When you send a TCP packet, it has a return address on it, just like a letter in the mail. But the protocol doesn't inherently check if that return address is actually yours. As a hacker, I can write someone else's IP address on the back of the envelope. This allows me to hide my identity, or even worse, launch reflected attacks. That is where I shout at a server, but I tell the server that you shouted at it. The server gets mad and attacks you, the victim, while I sit back and watch. So when you look at TCP/IP, don't just see rules, see opportunities. Every rule about reliability is a rule we can exploit to scan, flood, or spoof our way into a network. So, we've covered the language of the internet with TCP/IP. Now we need to talk about how computers actually find each other. This is DNS, the domain name system. Think of it this way. Computers don't know what Google.com or Facebook.com is. To a computer, those are just words. Computers only know numbers, IP addresses, like 142.250.183.46, DNS is the phone book that translates the human name into the computer number. When you type a website into your browser, your computer secretly shouts out to a DNS server, hey, where is Google.com? And the server replies, it's over at this IP address. Now here is the problem. When DNS was invented back in the 80s, the internet was a friendly place. It was built on trust. Your computer just blindly trusts whatever answer it gets, and that is exactly what we exploit. The classic attack here is DNS spoofing. It works like this. You are in a coffee shop, connected to the same Wi-Fi as your victim. When they type in mybank.com, their computer shouts out, "Who has the IP for mybank.com?" Normally, the real DNS server would answer. But as a hacker, I can be faster. I shout back, "I do. It's right here," and I give them the IP address of my fake server instead of the real bank. Their browser goes to my fake site, they type in their password, and I steal it. They never even know they left the bank's real network because the URL bar still says the right name. But there is an even cooler trick called DNS tunneling. This is how we sneak stolen data out of a secure network. Imagine you're in a super secure corporate office. The firewall blocks everything. No Facebook, no Gmail, no file uploads. But it has to allow DNS, otherwise the internet doesn't work. So what do? We take a stolen file, like a list of credit card numbers, and we chop it up into tiny pieces. Then, we hide those pieces inside DNS requests. We effectively send a message that looks like looking up creditcardpart1.hacker.com. The firewall sees a DNS lookup and lets it through. But on the other side, my server receives that lookup, records the credit card data, and stitches it back together. We are literally smuggling data right under the firewall's nose, disguised as boring internet traffic. All right, now we arrive at the main event, the OSI model. If you have ever taken a networking class, you probably fell asleep during this part. They teach it as this abstract, 7-layer cake of rules that tells computers how to talk to each other. But for us, for hackers, the OSI model isn't a set of rules. It is a map of attack surfaces. It tells us exactly where to hit a system to make it crumble. If you understand which layer a technology lives in, you automatically know which tools will break it. So we are going to walk through all 7 layers, starting from the bottom of the stack, the physical world, and moving all the way up to the screen you are looking at right now. I'm going to give you the theory, the analogy, and the exact way we exploit it. We start at the bottom. Layer 1. The physical layer. This is the real world. It's the cables, the fiber optics, the radio waves flying through the air, and the network cards plugged into the motherboard. Academics will tell you this layer is about voltage, light pulses, and bit rates. But a hacker sees layer 1 and thinks about breaking and entering. This is where digital security meets physical security. If I can walk into your server room and unplug the firewall, I have just successfully hacked you at layer 1. Think about the USB rubber ducky. It looks like a normal flash drive, but the moment you plug it into a computer, the computer thinks it's a keyboard. Because layer 1 hardware trusts other hardware, it accepts the input. The drive then types 1,000 words a minute, opening a terminal, downloading a virus, and executing it before you can even blink. That is a layer 1 attack. It exploits the physical connection. Or consider the Wi-Fi pineapple. It's a rogue access point that sits in a backpack. It listens for radio waves, which are layer 1 signals, and tricks phones into connecting to it instead of the real Wi-Fi. If you can touch the hardware or intercept the signal, the game is over. Moving up, we hit layer 2, the data link layer. This is the local neighborhood. This layer is responsible for moving data between devices on the same network, like 2 laptops connected to the same Wi-Fi switch. The currency of layer 2 is not the IP address, it's the MAC address. Every network card has a unique physical address burned into it at the factory. Now, the switches that run the internet trust these addresses implicitly, and that is their fatal flaw. The king of attacks here is ARP poisoning, or ARP spoofing. Here is how it works. Imagine you are at a dinner party. You want to send a secret note to the host, the router. You ask the room, "Hey, who is the router?" Ideally, the router stands up and says, "I am. Here is my MAC address. But I'm at the party too. I'm the hacker in the corner." So when you ask, I shout back, "I do. I am the router." And I send a fake ARP packet winking my MAC address to the router's IP. Your computer believes me because layer 2 is built on trust. Now, every single email, password, and photo you send to the internet goes to me first. I read it, maybe I change it, and then I forward it to the real router so you never know something is wrong. I am the man in the middle, and it's all because layer 2 doesn't verify who is speaking. Next is layer 3. The network layer. We are leaving the local neighborhood and entering the highway system of the internet. This layer is all about logical addressing and routing, This is where IP addresses live, IPv4 and IPv6. Routers operate at this layer, looking at the destination address on a packet and deciding the best path for it to travel across the world to reach a server in Tokyo or London. For a hacker, Layer 3 is about redirection and confusion. This is where we see IP spoofing. When you send a letter, you write a return address on the envelope. Layer 3 is that envelope. But nobody checks if you wrote the real return address. As a hacker, I can send a packet to a server, but write your IP address as the sender. The server gets the packet, gets confused or angry, and sends the reply or the error message to you, not me. If I do this with 1 million servers, they all start shouting at you simultaneously. That is a reflected denial of service attack. It's using the routing logic of the internet to flood a victim. We also see route injection attacks here, where a hacker tricks the routers into thinking they're the fastest path to a destination like YouTube. Suddenly, half the country's traffic to YouTube is flowing through the hacker's server. Then, we climb to Layer 4, the transport layer. This layer is responsible for how data is delivered, reliably with TCP or fast and loose with UDP. This is where ports live. When you run Nmap, you're scanning Layer 4. You are knocking on doors to see if anyone is home. But this is also where firewalls live. A firewall's main job is to sit at Layer 4 and say block port 80 or allow port 443. Understanding this layer allows you to bypass those firewalls. Attackers use techniques like fragmentation. Imagine you want to sneak a gun through a metal detector. You can't. But what if you took the gun apart? What if you sent the trigger through first, then the barrel, then the handle, all in separate boxes? The metal detector, the firewall, might look at the trigger and say, "That's just a piece of metal, go ahead." It looks at the barrel and says, "Just a tube, go ahead." But once all the pieces get past the firewall, the victim computer at Layer 4 reassembles them. It puts the gun back together, and now the malicious payload is inside the network. We are exploiting the rules of data assembly to hide the attack in plain sight. Now, Layer 5 and Layer 6, the session and presentation layers, are often skipped in tutorials because they are a bit abstract, but for us, they matter. Layer 5 is this session layer. It controls the conversation. It keeps track of who is talking to whom. Think of it like a wristband at a club. Once you show your ID at the door, you get a wristband. You don't need to show your ID every time you order a drink, you just show the wristband. In web terms, this is your session cookie. Hackers attack this with session hijacking. If I can steal your wristband, your session cookie, I don't need your password. I can just walk up to the server, show the stolen cookie, and the server thinks I am you. I am logged into your email, your bank, your social media, instantly. I exploited the session management. Layer 6 is the presentation layer. This is responsible for translation and encryption. It turns data into a format the application can understand, like JPG MP3, and handles the encryption, SSL/TLS. This is where the S in HTTPS lives. When you try to hack a secure website, you are attacking Layer 6. This is where we use tools like SSL Strip. Imagine you call your bank. You want to speak a secret code language, but I answer the phone and say, "Oh, sorry, the bank doesn't speak secret code anymore. Just tell me the password in plain English." You believe me. You say the password, and I write it down before passing it to the bank. SSL Strip tricks your browser into downgrading from a secure, encrypted HTTPS connection to an insecure HTTP connection. The encryption at Layer 6 is stripped away, and I can read everything. Finally, we reach the top. Layer 7, the application layer. This is what you see. It's the web browser, the email client, the video game. This is the user interface. And honestly, this is where 90% of modern hacking happens. Why? Because users interact here, and users are messy. At Layer 7, we aren't attacking the cables or the routing protocols. We are attacking the logic of the software itself. This is where you find SQL injection. A login box expects a name, but at Layer 7, I can type in a piece of database code instead. If the application isn't careful, it runs my code and dumps the entire database of passwords. This is where you find cross-site scripting, or XSS, where I make a website, run malicious code in your browser just by you visiting a page. And this is where phishing lives. The most dangerous vulnerability at Layer 7 is the human being. If I send you an email that looks exactly like your boss asking for a wire transfer, no firewall can stop that. No encryption can stop that. It's an attack on the application of human trust. So when you look at a target, don't just see a computer. See the layers. Ask yourself, can I touch it physically? That's Layer 1. Can I spoof the local traffic? That's Layer 2. Can I confuse the routing? That's Layer 3. Can I bypass the firewall? That's Layer 4. Can I steal the session key? That's Layer 5. Can I strip the encryption? That's Layer 6. Or can I just trick the application or the user into giving me the data? That's Layer 7. The OSI model isn't a checklist for an exam. It is a menu of options for destruction. Master the layers, and you master the hack. So there you have it. Whether you are mastering the handshake of TCP/IP or navigating the 7 layers of the OSI battlefield, remember this: knowledge is passive. Action is power. Watching this video won't make you a fucking hacker. Breaking things in a lab will. So here is your mission. Pick one layer we talked about today. Fire up Wireshark or Nmap on your home lab and see what it actually looks like on the wire. Don't just trust me, verify it yourself. If this deep dive helped you level up, hit that like button so the algorithm knows we exist. And let me know in the comments, which layer of the OSI model do you think is the most vulnerable? Layer 1, physical access, or Layer 7, user stupidity? I want to hear your take. Thanks for watching. Stay curious, stay ethical, and remember, one life, one shot. Make it count.